All right, so we're going to consider a function, the height function, as a function of time. H is going to be a function of time, and it's equal to 6 plus 2t. It's the height of a corn seedling measured in inches, t days after we plant it. So we're going to make a table of values for f of t over the domain from 0 to 3. So what is the height of the corn seedling at time t equals 0 when we first plant it? 6 what? 6 inches. Yeah. We're plugging in 0 for the t, so it's just 6. Yeah, 6 inches. And then what about when t is 1? What is h? 8, and then 10, and then 12 inches. So this says that you start at 6 inches and you add 2 inches every day, right? So this is a function talking about the growth of this seedling. But suppose I wanted to know a formula for how many days t it would take for the height of the seedling to reach some given height h inches. Like I say, okay, well, I can transfer my seedlings, from the grow light into the ground when they are 18 inches tall or something like that. How do I go the other way? I would make it equal to 18, but what if I wanted a function for any h? Not just for 18 in particular, but any height. I would like to know the time. Solve for t. So we just start with my equation, h equals 6 plus 2t, and you solve for t. Right, so start by subtracting 6. So I have h minus 6 equals 2t, and then divide both sides by 2, and you get t is equal to h minus 6 over 2. So you can take any height h and figure out how long it will take to grow the plant to that height. So I've changed it. Now h is the input. So it used to be that t was my input and I would calculate the output h. Now my input is h and I calculate the output t, time. So I interchanged the roles of the variables. Input became the output became the input. So if I create a new table of values, where now I'm plugging in h and getting out a t, if I plug in 6, what do I get for time? How long does it take to get to 6 inches? 0. And how long does it take to get to 8 inches? 1, and 2, and 3. Yeah, so how many people were figuring it out by plugging into this formula? Couple. How many people were figuring it out by looking at the table that we had before? A few. Okay, good. So you can do it either way. And it turns out that a function, if a function is a set of ordered pairs x, y, like here we have my function f, and my ordered pairs would be 0, 6, input, output, 1, 8, 2, 10, and 3, 12, right? Then the inverse of f, right? This is a new word. The inverse of f just reverses the components of the ordered pairs. So now 0, 6 becomes 6, 0. Right? So I have a point on the inverse function that switches the role of input and output. It just changes the ordered pairs. So this is 8, 1, 10, 2, and 12, 3. So inverse functions swap input and output. So that means that the domain of f is the range of f inverse, and the range of f is the domain of f inverse, right? Because the domain is the set of all inputs. So the domain of f is the set of all inputs into f. Those are going to be outputs from the f inverse, right? This other function that takes the outputs from the original function and gives you the input back. Okay, so we call these two functions 6 plus 2x and x minus 6 over 2. We call them inverse functions. The fact that g is the inverse of f is expressed by renaming g as f to the negative 1, but that does not mean f to the negative 1. This is repurposing an old notation to mean something new. Okay, so it does not mean f to the negative 1, does not mean 1 over f. You just read that as f inverse. the inverse of f. So if f of x is 6 plus 2x, g of x is x minus 6 over 2. Those are the two inverse functions that represent the corn seedlings. You would say, well, f is 6 plus 2x, and f inverse of x is x minus 6 over 2. Okay, so we'd rename g using f inverse, just to clearly show that those two functions have a special relationship. So when the variables don't represent a real-life quantity, in this seedling example they did, right? So I used t and h were the input and the output for the original function f. And when I did f inverse, I didn't rename the variables. I still had h and t, right? But when the functions don't represent a real world thing, we tend to use x as the input for both functions, the function and its inverse. Feels a little weird, but you'll get used to it. It's just sort of force of habit that x is supposed to be the input. It would be weird to say, let's use y as the input. And solving for the other variable. Yeah, yep, and we're going to do some more of it in the lesson. Yeah. Okay, so here's my same two functions, inverse functions, 6 plus 2x and x minus 6 over 2. What is f of 10? 26, yeah, you just go to the f function, replace the x with a 10, and you get 6 plus 2 times 10 is 26. So what is f inverse of 26? 10. Yes, how did you do it so fast? Because of the stuff we just went over, yeah. Inverse functions swap the role of input and output, right? So if f of 10 is 26, f inverse of 26 is 10. And you can double check it with the formula, right? If we put a 26 into this formula, you would get 26 minus 6 is 20, over 2 is 10. So it's like a round trip. If you think of this as if you compose a function and its inverse, it's like running two function machines in succession, like we did with composition last class. So I've got the f machine, and then I've got the f inverse machine. If I put an x in here, let's not use x, let's use 10. If I put a 10 into the f machine, out comes a 26. You take that 26 and drop it into f inverse, and out comes 10. So whatever x I put into f, if I run it through both machines, I get that same x back. Right? So more generally, I put an x in there. Out comes f of x, or some y, some number. If you put that into the f inverse machine, x comes back out. Whatever x you put in, if you run it through both machines, you get x back. So that's f of f composed with f inverse. Yeah. What does it look like with the equations? Good question. So that little circle means composed. So this is f of f inverse of x, right? F inverse of x has a formula. I'm going to substitute it in here. So this is f of x minus 6 over 2. Just making a substitution, replacing f inverse with its formula. So that means f of some stuff means take that stuff and plug it into the formula for f anywhere you see an x. So f of x is 6 plus 2x. So f of all this stuff is going to be 6 plus 2 times all that stuff. So now if I wanted to simplify this, those 2's cancel. And then I have 6 plus x minus 6, which is x. So when you compose inverse functions, you get x back. And we could do the other order also. If I wanted to do f inverse of f of x, replace f of x with its formula. So this is f inverse of 6 plus 2x. So that means take your 6 plus 2x and plug it into your F inverse formula. Yep. Yeah, yeah. So that's what we're trying to discover, that when you compose F and F inverse, you always get X. Yeah. So I'm doing out all the work, but you wouldn't have to once you see that. Yeah. So F inverse of 6 plus 2x, take your 6 plus 2x, plug it in for x. So we have 6 plus 2x, that's my x, minus 6 over 2. Right, the 6's cancel. I have 6 and minus 6, so those cancel. And then I have 2x over 2, which is x. So if you have two inverse functions, when you compose them in either order, you always get x. And think of it as running the function machine successively. Plug into f and then f inverse, or f inverse and then into f. They undo each other. It's like a round trip. Right? If you drop a 10 into the f machine, it'll give you a 26. Take that 26 and drop it into the f inverse machine, and it gives you 10 back. They're functions that undo each other. Okay, so here's the sort of really mathematical definition of an inverse function. F and g, if they are two functions, so that when you compose them in either order, f of g of x or g of f of x, both give you x, no matter what x you plug in, then the function g is the inverse of f, and it's denoted with that f to the negative 1. Read that f inverse. So f inverse of f of x equals f equals x, and f of f inverse of x equals x. The domain of f will be the range of f inverse, and vice versa. So part of what really helps ground your understanding of inverses is to think about real life examples. Okay, so let's do one more of those. We started with the corn seedling, and now we're going to talk about the time it takes to drive to New York City at a given velocity v. Okay, so t equals f of v gives the time in hours it takes to drive to New York City if you're going at an average speed of v miles per hour. So I didn't even have a formula, but what are my inputs for this function? V. V is miles per hour, right? And what is the output of this function? T, and that's hours. Good. So that's just a standard function. Input a speed, and it tells you how long it will take you to get to New York City driving that fast. So what does it mean if I say that f inverse of 3 equals 65? Yeah. So I have 3 as an input of this sentence, this mathematical sentence. If it's an input into the inverse function, that means it was an output from the function itself, right? So that 3 is hours. Okay, so 3 hours. So if I was going to read this, left to right, it would say that to get there in 3 hours, I need to drive 65 miles per hour. And that 65, it's an output of the inverse function, which means it was an input of the original function, so it's a speed. So in general, the inverse function tells you what speed to drive given a certain amount of time to get there, right? So it gives a speed necessary to arrive in t hours. Does that make sense? Okay. Okay, so another in context example here. This table shows the female literacy rate as a percent of the adult female population in various nations. We're going to define a relation where the domain, that's the set of all inputs, is going to be these 6 countries, and the range is the literacy rate. Okay. Is that relation a function? If you use the countries as a domain and the literacy rate of that country as the range, the outputs. Yeah, because no country could have 2 different female literacy rates, right? So each input has exactly 1 output. So yes, this is a function. Each input, exactly 1 output. All right, but what if I defined it the other way? What if I used the literacy rates as the input and the country as the output? It's not a function? Why not? Japan and Germany both have 99, so if I try to input 99, the function's like, if you think of this as a database, it's going to return an error, right? It's going to say, I don't know which country you want me to say. So this is a no, because 99 goes to 2 different things, right? 99 goes to Germany and Japan. 1 output, 2 different inputs. That makes it not a function. So in general, let's see if we can answer when is a function's inverse also a function. So let's examine tables and graphs for a couple of different functions. We've got x plus 1 and x minus 1 squared. So here's a table for f of x equals x plus 1. This is definitely a function, right? Passes the vertical line test. It's a function. Does it look like, so yes, because it passes the vertical line test. That's how you can tell if the graph of a relation is a function. What if I reverse the input and output, right? If this were my input column and this were my output column, do I have any problems with an input going to more than 1 output? No. Okay, so this is fine. It appears that f inverse is also a function. Okay, so how can we tell from the table? Because each y came from exactly 1 x. So each y is paired with exactly 1 x. And how can you tell from the graph? The vertical line test tells you that this guy is a function, but I want to know if its inverse is a function, right? If I swapped the roles of x and y, right? So right now that's y and that's x. What if the axes like traded places? It would still be a function. Yeah, like even if I rotate this thing, it's still a function because it would still pass the vertical line test after the rotation. So yes. And one way, well, we'll do the next one. Maybe it'll be clearer. Okay, so here's the graph of x minus 1 squared. Does that graph appear to be a function? Yes, it passes the vertical line test. Okay. Does the inverse of g appear to be a function? No. How can you tell? So I'll just write no. How can you tell from this table? The 4s, yeah. So when you switch the role of input and output, now I have 4 going to 2 different outputs, right? So now I have 4 goes to -1 and 3 if I switch the role of input and output. Okay, so the 4s. So how on the graph do I see this thing with the 4s? It's a parabola, yeah. Yeah, it would open sideways and then it would fail the vertical line test. So you can do that without picturing the reflection or the rotation. You could just do a horizontal line test, right? We could say, okay, well, the problem happens that here and here, those are the 4s. Those are the y values of 4. And it's the fact that that horizontal line hits the graph twice. 2 x values give you 4 in the original function, which means that if you swap the role of input and output, 4 would give you 2 different outputs. So how can you tell from the graph? Horizontal line test. Okay, because just like the vertical line test, you sweep a horizontal line through the graph. If it ever hits more than once, it is not, the inverse is not a function. So here it is written out again. If there is not a horizontal line that intersects the graph of the function f at more than one output, then its inverse is also a function. And we call a function whose inverse is also a function a one-to-one function, because it means that each x goes to exactly one y, and each y came from exactly one x. One-to-one correspondence between the inputs and the outputs. Don't think about the rotation. We're gonna talk about it's actually not a rotation. It's a reflection, because you're gonna switch the x's and the y's, and it's gonna cause a reflection, which will make this open sideways, but you'll see in a minute. Okay, so if I want to find the equation of an inverse function algebraically, we just use this procedure, which is exactly the procedure we used in the corn seedlings. Okay, so the only difference is that if this does not represent a real-world thing, you change the x's to y's and y's to x's, so that x will be the input for both the function and its inverse. Okay, when it represented a real thing, we didn't change the names of the variables, right? We didn't change h's to t's and t's to h's, because h means height and t means time. But here, my first step in finding an inverse is replace f of x with a y. So I'm going to have y equals 5x minus 6. And my step 2 is interchange x and y. Make your y's x's and your x's y's. So this would be x equals 5y minus 6. Now, if y stood for years and x stood for xylophones, right, you wouldn't make this switch. This is only in the generic case, right? If x and y stand for something in context, you wouldn't make this switch. Next step would be solve for y. So you add 6 to both sides and divide both sides by 5. Finally, replace y with an f inverse of x. And then you should show that if you compose the two functions, you always get x. I'm not going to do it. You can do it on your own. We did it in the earlier example. So here, this is the thing with how do you draw a picture of the inverse function given the function itself. So because the coordinates of the ordered pairs on f inverse are the ordered pairs of f, but we just swap the coordinates, you can create a graph of f inverse by first listing a few nice points in the graph of f. So looking at this picture, what are some points on there? Just go through nice grid points. 0, 1. 2, 4. Yeah. 3, 9. 5, 3, 9, yeah, 3, 9. That's it. That's all the nice grid points we've got. Maybe -1/2. Yep, it's 3, 8. Thank you. 3, 8 is the grid point. 2, 4, 0, 1. Oh, 1, 2. That's a good one. And -1/2. Okay. So the corresponding points on the graph of F inverse, you just swap the x and the y. Right? So I would have 1, 0, 4, 2, 8, 3, 1/2, -1, and 2, 1. Plot those points. And let's see, that's 1, 0, 4, 2, 8, 3, 1/2, -1, and 2, 1. Plot them with a nice smooth curve. And then this is going to go down like that, because it's going to approach the y-axis as opposed to the x-axis here. And what do you notice about the graph of F and the graph of F inverse? They're mirror images of each other, and where is the mirror? It's not the origin. It's this line. This line is the mirror. What's the equation of that line? Y equals x. Yep. So the graph of a function and the graph of its inverse are symmetric about the line y equals x. Imagine folding your graph along that line. Your two pieces would lie on top of each other. All right, so one more, we're going to find an inverse function algebraically. But take a look at this graph of x squared minus 1. Is it 1-to-1? No, it doesn't pass the horizontal line test, which means that its inverse is not a function. Right? So in general, we say this thing's not 1-to-1. Not 1-to-1, which means, so arrow means implies inverse, not a function. Okay. What would I have to do to this function to make it, force it to pass the horizontal line test? What could I do? Yes, but then it wouldn't be a function itself. Yeah. Yeah. So I want it to stay a function, but I want it to pass the horizontal line test. Like the what? Limit the domain. What does that mean? Just choose one half of it. Yeah, I'm just going to throw half of it away. I'm just going to say, just pretend that's not there. Okay. So now this is the function x squared minus 1, but I'm restricting the domain to x is only bigger than or equal to 0. I just ignore everything else. Okay. And the reason I do that is because now it'll pass the horizontal line test, and I can find a formula for its inverse. So I have the equation, so choose half. Right. And you could choose either half. It's just typically easier to work with positive numbers, so I got rid of the negative ones. So now I have the equation y equals x squared minus 1. If I want to find a formula for the inverse function, swap the x's and the y's, and solve for the y. So I add 1 to both sides. And then what do I do to get y by itself? Square root. So y equals square root of x plus 1. And I'm only going to use the positive square root. Typically, I would write plus or minus there. But that would make this not a function, right? If I had an input of x and I got a positive and a negative output, not a function. So I'm just going to use the positive one because of how I restricted the domain. So f inverse of x is equal to the square root of x plus 1. So if I'm restricting my domain to x is positive here, the domain of the regular function is all positive numbers. That should be the range of the inverse. That should be the range of the inverse. That's why I chose the positive square root. Right? If my domain of the original is positive numbers, the range or the outputs of my inverse should be positive numbers. So now when I graph the square root of x plus 1, it's this guy in green, and it is the reflection of x squared minus 1 graphed in red there, with its domain restricted. All right. Everything you need to know about inverses in 30 minutes. Now I'm going to have you do some practice.